Okay, Assalamualaikum warahmatullahi wabarakatuh and good. Salam sejahtera. Okay, today we'll discuss on lecture 6, which is integer number theory. Actually, you already seen this topic in your which is one subject from jabatan apa? Rangkaian. Maksudnya kita ada number theory kat situ. Kamu dah belajar. But here we discuss it in discrete mathematics punya perspektif macam tu. Okay, so now this is the lecture content and this lecture quite a long notes. Okay, so this is an introduction, and number 2, divisibility and modular arithmetic, integer representation, then prime and greatest common divisor. Okay, as an introduction, the part of mathematics devoted to the study of the set of integer and their properties is known as number theory. Okay, we will first introduce the notion of divisibility of integer, which we use to introduce modular arithmetic. Okay, what is division of integer by a positive integer produce a quotient and a remainder. Okay, working with this remainder lead to modular arithmetic, which play an important role in mathematics and which is used throughout computer science. Okay, what does it mean? Okay, when one integer is divided by a second non-zero integer, the quotient may or may not be an integer. Okay, for example, this 12 divided by 3. Okay, and the answer is 4. But when 11 divided by 4, we found that this is not an integer, right? It is 2.75. Okay, this lead to the definition of division. Okay, because it contain remainder, baki kat situ. Okay, if A and B are integer with A is not equal to 0, we say that A divides B, A divides B, which is A divides B. A ni terbahagi dengan B, is an integer. When A divide B, we say that is a factor or divisor of B, and B is a multiple of A. Okay, the notation, okay, A divides B. Okay, denotes that A divides B, and this means like this. Okay, it is not equal to A divide B macam ni. It is not that like that. Okay, so A divides B. Maksudnya A ni terbahagi dengan B. Okay, so some of basic property of divisibility of integer are given in Theorem 1. Okay, here. If we have A divide B and A divide C, then A divide B plus C. This means, okay, A divide B and A divide C, and we can tell that, okay, when we have plus here and it is B plus C. Okay, A B plus, kepala cakap C, but when right, become E. Okay, so B plus C divide, okay, A divide B plus C like this. Okay, if A divide B, then A divide B C for all integer C. Okay. A divide B, okay, for all integer C. Okay, ni kalau kita ada darab lah pula. Okay, maksudnya kalau kita ada A divide B, then kalau kita ada something yang times C dekat luar ni, maksudnya is equal to C, B. Okay, kita bahagi dengan A macam tu kan. So A divides B, C. Okay, if A divide B and B divide C. Okay. So kita ada ayat yang ketiga tu bermaksud A divide B and we have another this B divide C. Kalau kita times ni kan kita dapat kan macam tu. Kita boleh matikan. So it become A divide C. Okay. So this is the theorem 1. Okay. Division algorithm. When the quotient may not be integer, for example, 11, kita bahagikan dengan 4, we get 2.75. This lead to theorem number 2. What is theorem number 2 here? Let A be an integer and B a positive integer. Then there are unique Q and R, with R is between 0 and D such that A is equal to DQ plus R. Okay, what is this? In the equality given in division algorithm, D is called a divisor, A is called a dividend, Q is called a quotient, and R is called a remainder. This notation is used to express a quotient and remainder. Okay, Q is equal to A divide D. R is equal to A mod D. Okay, what is it? Okay, let us look at this example. Okay, what are the quotient and remainder when 101 is divided by 11? Okay, so kita ada 101. Okay, kita nak bahagi dengan 11. Okay, 11 kali 9, it become 99 here, right? So, the remainder baki dia kat sini ialah 2. So, here, we know that 101 is equal to 11 times 9. 11 times 9 plus the remainder here is 2. Okay, 2 ni ialah remainder. So, hence the quotient when 101 is divided by 11 is 9 and the remainder is 2. So, when we want to form it in the previous here, A is equal to DQ plus R. Okay, so here A is equal to DQ plus R. Okay, this is the quotient and this is the remainder. And 11 is the dividend just now. And what is A here? A is what? Okay, A is equal to, okay, D is called, A is called, oh, A is dividend, Q is quotient, R is the remainder. Okay. So here, integer representation of, okay, here, integer representation of integer. Okay, base conversation. Okay, in everyday life, we use decimal notation to express integer. For example, 965 is used to denote this kind of number. Okay, sebab 5, 6 kali 10 ni 10 punya tempat kan. 9 times 10 power of 2 is 100. Maksudnya 900 which is tempat kepada ratus kat situ kan. However, it is often convenient to use bases other than 10. In particular, computer usually use binary notation with 2 as the base. When carrying out arithmetic and octal base 8 or hexadecimal base 16 notation when expressing characters such as letter or digit. In fact, we can use an integer greater than 1 as a base when expressing integer. Okay, here. Theorem number 3. Let b be an integer greater than 1. If n is a positive integer, then it can express uniquely in the form n is equal to a k b k plus. Okay, ini kita boleh express satu nombor tu dalam bentuk macam ni where k is a non-negative integer. A0 until ak are non-negative integer less than B and AK is not equal to 0. Okay, here. Binary expansion. Choosing 2 as the base give binary expansion. Okay, this is the binary notation. Each digit is either 0 or 1. In other words, the binary expansion of integer is just a bit string. Binary expansion and related expansions that are variant of binary expansion are used by computer to represent and do arithmetic with integer. Okay. What is the decimal expansion of the integer that has? Okay. Dia nak cari decimal punya bentuk yang asal 10 daripada binary punya number. Okay. So, kita boleh guna yang theorem yang sebelum ni lah. Yang ni. Okay. So, yang ni kita kena buat, okey, yang paling kecil yang belakang tu kena darab dengan 2 kuasa kosong. Lepas tu yang kedua darab dengan 2 kuasa 1. Yang ketiga 2 kuasa 2 darab dan seterusnya sehinggalah satu ni darab dengan 2 kuasa 8. So semua ni kita tambah. Okey, so yang depan ni represent kita punya binary number. Kosong just now. Okay, so it become 351 for decimal expansion. Okay, so for octal and hexadecimal expansion, among the most important bases in computer science are base 2, base 8 and base 16. Base 8 expansion are called octal and base 16 expansion are hexadecimal expansion. Example 3 here, what is the decimal expansion of the number octal? Okay, this is the octal number. Okay, we can find that the notation that represent the octal which is here, yang subscript yang kat bawah tu yang kecil tu 8. 8 means that this is in octal punya base, which is base 8. Okay. Kalau kita ada 7016 base 8, we want to expand it into decimal. Okay, so now like previous by using the theorem 3, okay, here we have to times it with the 8 asas 8. Yang paling hujung ialah 8 kuasa kosong until here 8 kuasa 3 and it will time with 7 then 0 and 1 then 6. We sum it all together, then we get 3, 5, 9, 8 for this. Okay, this is easy, right? Like a recap from the previous lecture from your other subject. Okay, so for 16, different digits are required for hexadecimal. Okay, so we know that our digit consists from 0 until 9 only. But when we want to represent it until 16, so we have to use letter A until F, which is A represent 10, B 11, C 12, D 13, 14 and 15 for F. Okay, what is the decimal expansion for this hexadecimal expansion here? Okay, so when we have to times it by using the theorem previously, which is yang belakang sekali darab dengan 16 kuasa kosong until yang depan sekali 2 ni darab dengan 16 kuasa 4. Okay, so now for A, E and B, we have to find the original value for that particular alphabet, which is A is 10 and E is 14 and B is 11 for here, and we sum it all together, we get for decimal expansion is 175,627. Actually you can use your calculator to convert, right? If you don't have calculator while exam, your calculator suddenly don't have the battery or other technical issues, so that you have to know how to calculate it by using manual calculation. Okay, so this is base conversion. We will now describe an algorithm for constructing the base B expansion of an integer. First, divide n by b to obtain a quotient and remainder. Okay, this is quotient and we obtain remainder. Okay, here The remainder A naught is the rightmost of digit in base B expansion of n. Next, divide Q naught by B to obtain. Okay, so now here A1 dia tak boleh lebih besar daripada B, between 0 and B. We see that A1 is the second digit from the right in the base B expansion of n. Continue this process successively dividing a quotient by B, obtaining additional base B digit as the remainder. This process terminates when we obtain a quotient equal to 0. It produces the base B digit of n from the right to the left. Okay, here, this is an example 5. Find the octal expansion from this decimal expansion. Okay, from decimal to octal. So, kita kena buat macam ni. Okay, kita ada 1, 2, 3, 4, 5. Kita kena bahagi dengan 8 because we want to find the octal punya expansion, right? So, when we divide it by 8, we found that it is 1543 dan bakinya ialah 1. Then, divide again our value here. Letak dekat bawah. Okay, maksudnya macam ni. Ambil value ni. Okay, we put it down. Okay, so we divide it by 8 again. So we found 192 dengan baki 7. Then bring 192 to the front. Then we divide by 8 again. Then we found that the remainder is 0 for 24. Then we put 24 in front. And repeat the process, we found that the remainder also 0 until we get the value here. Nampak tak kat sini? The successive remainder that we found that 17003 are the digit from the right to the left. 1, 2, 3, 4, 5 in base 8 ni. H. Kita punya jawapan nanti maksudnya daripada kalau kita nak tulis tu 1 yang kat atas ni tulis jadi belakang dan 7. Lepas tu seterusnya kepada 3. Tulis je di hadapan sekali. Maksudnya macam tu. Okay. So daripada atas ni dia akan turun. Maksudnya dia akan jadi macam ni. Okay. So here. This is hexadecimal expansion. How we find the hexadecimal from decimal punya expression. Like previously we bahagi dengan 16 pula. Sama juga yang belakang ni we bring it forward. Okay, nampak tak? We bring it forward. Okay, so yang ni pun sama. Okay, sehingga kita dapat dia punya baki ni. Okay. So, baki ni tulis daripada belakang ke depan. But here we have to remember 10 is not 10 in hexadecimal. It is A. And 14 is represent as E. And 3, then 11 as B, then 2. Okay, this is the hexadecimal expansion for this particular decimal number. Okay, so here is from binary, form a binary expansion from decimal like previously. Sama juga prosesnya. Kamu boleh cuba sendiri. Sama juga tulis daripada atas tu. Maksudnya daripada belakang ke depan bila kita nak tulis tu. Okay. This is also can be calculated by using your calculator, right? Okay, so now this is example 8. Okay, we want to find this. Daripada we find the binary daripada dua ni. Okay. So, we can find the binary. Kenapa binary macam ni? Okay, so sekarang daripada 765 ni kita nak cari dia punya binary notation. Kita kena buat macam ni. Untuk 7, 6 dengan 5. Okay, so kita kena letak dia kepada 3 tempat kat situ. Okay, 3 binary digit. Mesti ada 3. So, kalau 3, 5 ni, 5 ialah 101. Kenapa 101? Ialah 2 kuasa 0 tambah, tambah 2 kuasa 2. So, 4 tambah 1 ialah 5. So, this is the value for 5. And 6 is 110. And 7 is 111. So, we combine all together. So, we get this is as a binary expansion for decimal octal, and for this hexadecimal, like which is D represent D as a binary. This is D tu nombor berapa? D ialah nombor A, B, C, D, 14 kan? So, and this is the 8 punya representation in binary, and this is A representation in binary. So, we put it here, and this is as a D just now. So this is the binary notation from the hexadecimal. Okay, so here example 9. Kalau kita ada daripada binary pula, kita nak convert kepada octal dengan hexadecimal. Okay, so sekarang sama juga. Kalau kita nak convert kepada octal, kita bahagi kepada 3, 3, 3, 3. 1, 2, 3. 3, 3. Macam tu. So, bila kita letak 3, 3, 3 dan depan sekali ialah 0, 1, 1 ni. So, tukar dia kepada bentuk kita kena cari. Maksudnya kalau 3, 3, 3 tu maksudnya tukar dia. Kita dapat yang ni ialah 4, ini ialah 7 dan ni ialah 2. Okey, dan seterusnya. So, kita dapat kepada octal, dan hexadecimal pun sama, kita kena bahagi kepada 4, 4, 4 so that we get this back. Okay. Here, for prime and greatest divisor. So what is prime? Prime number. Okay. Perdana, right? Every integer greater than 1 divisible by at least 2 integer, because a positive integer is divisible by 1 and by itself. Positive integer that have exactly 2 different positive integer factor are called prime. And integer p is greater than 1 is called prime if only positive factor of p are 1 and p. Okay, a positive integer that greater than 1 and is not prime is called composite. Kalau bukan nombor perdana, kita panggil dia sebagai composite number. Okay, the integer 7 is prime because it's only positive factor are 1 and 7, whereas the integer 9 is composite because it is divisible by 3. Okay, dia boleh dibahagi dengan 3. Okay, so we call a composite number. Okay, so now this is fundamental theorem of arithmetic. Every integer greater than 1 can be written uniquely as a prime or as the product of 2 or more prime, where the prime factor are written in order of non-decreasing size. Okay, for example here, prime factorization of integer. Okey, kalau kita ada 100, kita nak cari prime number dia, kita boleh dapatkan dia dengan 100 ialah, okey. Kalau dia 100 macam ni. Kalau kita nak cari 100 ni macam ni. Kita bahagikan dengan prime number yang pertama ialah 2, right? 100, okey. 100 sama juga dengan 2 kali berapa? 50. Okey. So sekarang kita cari yang paling kecil lagi. Wait, macam mana? 2 kali 50 kali berapa kali? Sebab ni yang ni dah prime number. So leave it as 2 saja. Jangan ganggu. Okay. So 50 ialah 2 boleh bagi dengan 2 kan? Nombor yang prime paling kecil ialah 2. 2 kali 25. Okay. So now here. Ini pun dah prime number. So kita tulis balik 2 kali 2. Okay. So 25 ialah berapa? Dia tak boleh bagi dengan 2, dia tak boleh bagi dengan 3 dan dia hanya boleh bahagi dengan 5, right? 5 is also a prime number, so it is 5 times 5. Okay, macam itulah kita nak cari dia punya prime factorization. So kita dapat 2255 for this 100. Okay, same okay, yang ni tak dapat cari sebab 641 ni memang prime number. Okay, so for 999 ni pun dapat juga. So kita cari guna benda yang sama. So until the last one here, 37 is a prime number. So leave it as a 37. We can't find the division of that number. Okay, for 1024, okay, it is actually 2 power of 10. Okay, we find it by using macam ni juga. Kita cari macam ni juga. Okay, so here. For theorem 5, if n is a composite integer, then n has a prime divisor less than or equal to set n. From theorem 5, it follows that n integer is prime if it is not divisible by any prime less than or equal to its square root. Okay, this leads to brute force algorithm known as trial division. Okay, to use trial division, we divide n by all prime not exceeding set n and conclude that n is a prime if it is not divisible by any of these prime. In example 12. Okay, so we look at example 12 here. Okay, the only prime not exceeding 101 is, okay, so bila kita cari set 101, dia ialah yang ni. Okay, so kita tahu yang paling besar dia ialah 10. So kita tahu yang tak exceed nombor perdana yang tidak melebihi 10 ialah 2, 3, 5 dan 7. So because 101 is not divisible by 2, 3, 5 dan 7, dia tak boleh bahagi dengan 4 nombor ni. So we can conclude that 101 is a prime number. Tak perlulah kita nak buat seterusnya. Lepas 7 berapa? 11. Bahagi lagi. Lepas tu kita nak cuba lagi. So tak perlu. So by using previous punya theorem, kita dah cari square root of 101 ni, kita dapat 10. So kita just consider nombor yang lebih kecil daripada 10 saja untuk cari dia punya prime factorization. Kalau dia tak dapat, maksudnya sampai 7 tak dapat, so kita tak perlulah buat 11 sampai seterusnya kerana it enough. So we can conclude that 101 is a prime here. Okay, so here kalau 7,007 ni pun kita agak confused juga kan, kita tak tahu dia ialah nombor prime number dia ialah apa. So kita cari dia punya square root. Square root dia ialah 83. Banyak ni kan, betul tak? So kita buat satu per satu. Perform the division of 707 ni dengan kita buat divide by 2. So kita tak dapat jawapan. 2, 3, 5 kita tak boleh dapat. So bila kita buat 707, bila dia divide by 7, kita dapat 707 ni, kita dapat 101. So kita dapat dah 7 kat situ. Okay, so sekarang ialah 7 kali 1001. Okay, so now kita consider yang belakang ni pula. 1001 ni kita cari dia punya, okay, kita cari dia punya prime numbers. Just now kita dah sampai 7 kan? Okay, so now beginning with 7. Okay, so sekarang kita bahagi dengan 7. So kita tak payah consider 2, 3, 5 tu, tak perlu. So kita consider 107, kita divide by 7. So kita dapat 143. So kita dapat macam tadi caranya. 7 kali, kat sini ialah 7 kali 143. Okay. This is the prime number yang kita dapat. So now 143 ni pula. 143 ni kita nak bahagi dengan 7 tak boleh bahagi. So kita leave 7 tu. So kita cuba buat 11 pula. Kat sini kita bahagi dengan 11. So kita dapat, bila kita bahagi dengan 11, kita dapat 11. Okay, sama juga dengan 7 kali 11 kali. Okay, bahagi dengan 11 kita dapat 13. Okay, so now because 13 is a prime, once we get the prime number, so we stop the process. So now we know the prime factorization for 707 here. 7007 is 7, 7, 11 and 13. So ini ialah 7 kuasa 2, 11 dan 13. So this is the prime factorization. Okay, kalau faham boleh tengok balik. Kalau tak faham, tengok ulang balik. Okay, so now for Next is greatest common divisor. Okay, the largest integer that divide both two integer equal greatest common divisor of this integer. What is the greatest common divisor? Let a and b be an integer not both 0. The largest integer d such that d divides a and d divides b is called the greatest common divisor. Okay, so sekarang greatest common divisor ni macam kalau kita ada satu nombor kan. Contohnya 6 terbahagi dengan 2. Okey, lagi satu ialah 8 dengan 2. Okay, so now we know that this is the greatest common divisor for 6 and 8. Macam itulah maksudnya. Greatest common divisor. Okay, so now example 14. Okay, what is the greatest common divisor of 24 and 36? Okay, dia berkongsi berapa common divisor. Okay, so now for 24 and 36, dia punya positive common divisor dia ialah dia boleh bahagi dengan 1, 3, 2, 3, 4, 6 dan 12 untuk ni dan yang ini. So, for this, lepas kita senaraikan, kita nampak yang paling besar dia ialah 12. Okay, kita cari dia punya greatest common divisor yang sama kan. Okay, so kita tahu dia boleh dibahagi dengan 12. What is the greatest common divisor of 17 and 22? Okay, so sekarang untuk 17 dengan 12 kita tak ada common divisor yang sama. Kan betul tak? Sebab kita tak 17 tak boleh bahagi dengan nombor lain kecuali diri sendiri. But here 22 ni boleh bahagi dengan 2 tapi dia tak ada common divisor with 17 just now. So our greatest common divisor kalau dia tak ada yang common yang sama, so 1 is our greatest common divisor. Okay, so now here relatively prime. A and B are relatively prime if their greatest common divisor is 1. Okay, so this 17 and 22 is, we call it as relatively prime. Okay, because GCD for these two number is 1. Okay, so now for example 16. Okay, what is the greatest common divisor for 120 and 500? Another way to find the greatest common divisor, find two positive integer, is to use the prime factorization of this integer. Suppose the prime factorization of the positive integer A and B are, okay, so kita boleh senaraikan prime factorization macam yang tadi kita buat contoh yang sebelum tadi, macam mana nak cari prime factorization. So kita senaraikan untuk A dengan B. Okey, bila kita senaraikan, lepas tu kita boleh cari dia punya GCD ialah dengan mengambil minimum value from A1, B1 ni, yang mana minimum kita ambil dia. Okay, for P2, A2 dengan B2, minimum dia yang mana kita ambil dia. Okay, so for example here, example 16, contohnya kat sini. Kita nak cari greatest common divisor for 120 and 500. Okay, so now here, kita tahu bahawa 120 dia punya prime factorization. Macam mana cari prime factorization? Tengok balik contoh sebelum ni. Okay, so kita tahu prime factorization untuk 120 ialah 2 kuasa 3, 3 kuasa ke 1 dan 5 kuasa 1. Dan here ialah 500 ialah 2 kuasa 2 dan 5 kuasa 3. Dia punya prime factorization. Okay, so now for GCD, by using the previous punya example tadi tu kan, kita tahu 2 kat sini kan, 2 ada 2. Kat sini pun ada 2 juga. Okay, so now 2 kat atas ni yang power dia ni ada 3 dengan 2. And for 3 here, but here there is no 3, but we can put, okay, 1 ni represent yang atas ni, but there is no 3 for here, so we put it as 0 kat sini. Okay, so now we look at 5 punya base pula. 5 ni, okay, yang atas ni kuasa 1 dan yang bawah ni kuasa 3. So ambil yang paling kecil for all of these. So we find that 2 power of 2 times 3 power of 0 times 5 power of 1. Okay, so 2 kuasa 2, 4. 4 campur 1 ialah 5. Macam mana dia boleh dapat? 2 kuasa 2. 2 kuasa 2 ialah 4. 4 kuasa 2 kuasa 2, 4. Okay, so here is 3 kuasa 0 ialah 1. Okay, betul lah. 4 kali, ni kali saya ingat tambah tadi, kali 1 kali 5. So we get 20, sorry. Okay, prime factorization can also be used to find the least common multiple. Least common multiple. What is least common multiple? Least common multiple of the positive integer a, b is the smallest positive integer that is divisible by both a and b. Okay, so here we denote it as LCM. Suppose that the prime factorization of positive integer a, b ialah yang ni, but here we look at the maximum a1, b1, maximum dia. Okay, for example here, okay, kita nak cari prime factorization untuk number 95256 ni, kita cari by using the previous punya, nak cari prime factorization. Okay, so now here pun sama juga, kita nak cari dia punya prime factorization dulu sebelum kita nak cari least common multiple. So here kita cari notation yang sama, 2. Sebelah dua-dua ada 2 kan? 2 kuasa 3 dengan 4 kat sini. So kat sini tak ada 3. Kat sini ada 3, 2 tempat. So 3 kuasa 5 dan 3. Then there is 7 there, but there is no 7 for 4, 3, 2. So we have to pick the maximum value 2 kuasa 4 kali dengan 3 kuasa 3 dan kali dengan 7 kuasa 2. So that we get the LCM for these two number is 190, 190, 190,512. Okay, so now the relationship between these two number ialah apa? Okay. The relationship between these two number ialah GCD kali dengan LCM. So kita dapat dua number ni. Okay. So now here the excluded algorithm. Okay. Computing the greatest common divisor of two integer directly from the prime factorization of this integer is inefficient. The reason is that it is time consuming. Then we will give a more efficient method of finding the greatest common divisor called equated algorithm. This algorithm has been known since ancient time. Okay, it is named as Greek, which is Euclid, who include description of this algorithm in his book, the Element. Okay, this is the algorithm 1, which is Euclidean algorithm. Okay, we want to input positive A and B, then we want to find the output GCD AB. Okay, this is how he derived the algorithm to find this GCD for AB, which is X. We can find the X by using this algorithm. Okay, so this is example 18 by using the Euclidean algorithm. Okay, so now here, okay, find the greatest common divisor using the Euclidean algorithm. Okay, so now 662. Okay, now yang dalam ni ialah kita ambil nombor ni 414. 414 kali berapa dapat? 662. So 414 kali 1 tambah 242 kita dapat 662. Okay, so now here, from here, like previously we buat yang cari yang base just now tu kan. So yang ni letakkan dekat depan. Okay, put it in front. So berapa kali untuk dapatkan 414. So 248 kali 1 campur dengan 166. So kita dapat value ni. Okay, so now we repeat the same process here. We put it in front. So kat sini ialah okay, here, which is 16666 kali 1 campur 82, kita dapat 248. Okay, so now here we get the value for this is B2 because 2 is the last non-zero remainder. So kita dapat value dia, GCD dia dekat sini, non-zero remainder tu kat situ. So this is how we find the greatest common divisor by using Euclidean algorithm. Okay, so now here, an important result we will use throughout the remainder of this section is that the greatest common divisor of two integers a and b can be expressed in the form of sa plus tb, where s and t are integer, okay, which is the linear combination for this. Okay, so now we want to find the linear combination for this. 6, 14 kat sini. So kita tahu bahawa kat sini, for example GCD ialah 2. So sekarang 2 ialah, dia punya linear combination ialah, so kita kena letak 2. Yang ni 6 kan, 6 dengan 14. So negatif 2 kali 6 campur 1 kali 14. So kita dapat 2. This is what we call the linear combination to get the GCD value kat sini. Okay. Kat sini theorem 8, Benzold theorem. Here. Positive integer that there exists integer s and t such that GCD a be sa plus tb. Okay, so now this is how we find the extended Euclidean algorithm. We want to find the linear combination of that. Okay, so now we have these two number. Okay, so sekarang kita ada 252 dengan 198. So sekarang kita letak yang paling besar dekat luar. So yang 198 ni kali berapa? Dapat 252. So dikali 1 campur dengan 54 kita dapat 252. So seterusnya buat proses ni until we get the 0 as a remainder. So the last one here is 18. Okay, using the next last division which is the here third, we can express GCD 252 158 is equal to 18 as a linear combination of 54 and 36. 54 and 36. Okay, so now here kat sini 1, 3, 1. Okay, so kita guna yang ketiga ni. Kita rearrange 18 letak dekat depan. So sekarang kita ada 36 ni. Okay, so 54 tolak 1 kali 36. Ini as equation 31. Okay, so the second division 36 ni. Okay, dia akan jadi, okay, kita ambil daripada, ni. Kita ambil daripada 2 ni, daripada 2 ni. So kita dapat, here. So as a 2.1. Then 2.1 ni we substitute in 3, 2 just now. Okay, so kat situ ada 36 kan? So kita substitute yang ni, letak kat value 36 just now. Okay, yang ni, 36 ni kan? Okay, so now we get 3.2. Okay, I will explain this later in your tutorial. Okay. For more detail, okay, the first division 1, okay, yang ni daripada first division ni, yang ada 54 ni. Okay. Here, we rearrange to get 1.1. So here, substitute 1.1 yang ada 54 ni kepada yang ni 3.2. So that we get here, 4 kali 2, 52. Tolak 5 kali 1, 98. So this is the linear combination which is 4 and negative 5. Okay, so this is the step-by-step illustration for extended Euclidean algorithm. Just now daripada ni kita ambil 3. So jadi 3.1 ni ada 36 ni masuk kat sini. Okay, kat sini 36 ni kita gantikan dengan value sini yang nombor 2. Okay, so kita dapat 3.2. So daripada 3.2 ni kita ada 54. So daripada equation yang pertama ni kita ganti dia dekat dalam 54 ni. So kita dapat here the linear combination. How to know that we already find the linear combination? Bila kita tengok kat sini dia dapat 252 dengan 198 kat sini. Okay, so yang ni ialah S dan T yang kita cari tadi. Okay, so here that we cover all the lecture, then next lecture will be induction and recursion. And this topic will be asked in your midterm exam, ya. Okay. Yang sebelum ni saya cakap sampai function dia salah, sampai tutorial 6. which is not include tutorial 5 in your midterm. Okay, so thank you until here. Okay, good luck and Assalamualaikum.